So, sorry for the delay. Let us begin. My name is Leonid. I will introduce myself a little bit later. Just to understand the audience, like, what's your expectations from this talk? Kind of, have you ever trained TensorFlow models before? How much of you? Oh, some of you, great. And have you trained any like machine learning models before? I kind of have the feeling that TensorFlow guys, I got more answers than like for the second question. Okay, so I'll try to adjust myself. If you will kind of like, let's do it more interactive. If you don't kind of like understand something, please like let me know. Or if you feel that I'm talking about like too basic stuff, again, kind of like give me feedback so that like, you know, it's kind of like more valuable for you. Yeah. So kind of like the idea of this talk is actually intended for people who have some experience with machine learning, and like if the team has been training machine learning models before, like in the on-premise data center, on the, you know, like your own hardware, I was going to explain a little bit why would you like to move to the cloud and what you should take into account. But we can a little bit, so actually is this topic relevant to you guys? Or we can try to readjust on the fly and talk a little bit about the different things. I kind of like have a little bit weird feeling. So like, it's actually like training ML models on a regular basis, like in production, something you're dealing with in your regular life. Yes, no, we don't care. We just sit here and kind of like, I mean, guys, I can just show you the presentation and that's it. But like, if you would give me some feedback, I could readjust a little bit and, you know, talk about things that are relevant to you. Does it make sense?
I guess our backgrounds are very different.
Okay.
So I think your question is relevant in this case because I can talk about my experience, which is non-experience. I mean, I don't have any experience with it, but there might be some guys who have. So I think if you could just, you know, wrap machine learning in 10 minutes and then, you know, do your stuff. That would be great.
Okay, that's good. Sorry for, I mean, I will wrap machine learning in 1 hour on my second workshop. I have like at 12:30. So actually, if you're interested in this thing, I will kind of like a little bit talk about some basics you need to know before initiating any ML project and kind of like main mistakes you can do as a business owner, as a PM, as a product owner. So if you're interested in this thing, please come. But thanks, I kind of like get the better feeling now, and that's what I, you know, kind of like I had some suspicious. So let's do the following. I will like click slides a little bit faster. If you have questions, please interrupt me at the slides. And then we will kind of like cover it a little bit deeply. And I will try to focus a little bit more on distributed TensorFlow and training and distributed training, like just to explain how it works. It's the second piece of this presentation, okay? And again, please be kind of like more interactive. Interrupt me, ask questions so that kind of like, you know, it makes more sense for you guys. I mean, let's make it like not like less official. And yeah, kind of like the initial idea was to talk, oh man, I kind of, what is this? Is this the right presentation? I hope so. Okay, sorry. Okay. So the first idea, why sometimes machine learning teams want to move to the cloud? And there are like a few specific use cases. Like, first of all, any cloud, and kind of like, you know what cloud providers are about. Who doesn't know? Okay, then just ask me. I mean, please, let's make the rule of this hour. If you don't understand the term, ask me. Because sometimes just my English is horrible, and you know, you might not just understand what I'm saying. So the cloud providers, actually, it's kind of a little bit kind of like new model of doing software business. When you get managed services and managed infrastructure, and for example, you can, like the easiest use cases, you can come to the cloud provider like AWS, Google Cloud, Azure, or like, I mean, more players, and for example, rent a single VM. So you don't need to buy it now. You can just rent it, and you get like a virtual machine. So VM is a virtual machine. And then you can do whatever you want with that. And then the main idea is kind of like the principal pay as you go. So you rent a virtual machine for 1 hour, train your machine learning model, and then you give it back. And you can do more complex things because you get managed services like databases, security services, networking, and these kind of things. So the idea is now you don't need to care about infrastructure because the cloud provider takes care for you and gives you certain APIs like to configure it and like deal with that. And that's actually a nice thing because if you train models, the problem is that first of all you need scalability and flexibility. What do I mean by scalability? You don't have flat load on your hardware. Sometimes you have a lot of business and then you need a lot of models to train because you're going to deliver your product. Or you just, you have finally got the data, collected the data, cleaned the data, now what you want to train, and that's this spike when you need a lot of computational power. At this moment, you need a lot of machines, and that's you can't have it in your own data center because otherwise they would be idle and you won't invest in it and it doesn't make sense. So that's why cloud is a good option for teams who are in machine learning model business. Machine learning training. The second thing is flexibility. Because when you deal with email, you never know in advance what type of hardware do you need. Do you need GPUs? Do you need more CPUs? Do you need more high memory machines and these kind of things? And again, with the cloud, you can choose whatever hardware you need at this specific moment and experiment with that. And you are not locked in because with your own data center, you go, you buy a GPU, you invest money, and now you need to deal with this specific GPU, and you don't know was it actually a good GPU for you. I was in this situation too, and we with my team were sitting and thinking, okay, what should we order for the next year? What kind of hardware we have a budget? And we don't know because it's very hard to say, and we can do any tests, and we are actually not hardware specialists. And with the cloud, you can take this NVIDIA GPU, take that NVIDIA GPU, try it yourself, make some decisions, and then move on. So this is the reasoning. But enough about that. Short thing about me: I've been working with Yandex. I've graduated from my MIPT quite a while, more than 10 years ago. Then I've been in different roles, in analytics and later in ML. As engineer, as PM, and now back as engineer. I've been working for Yandex, for HHRU, and other companies, and now I'm with Google in Munich. And the first piece, if you want to train a model by renting a virtual machine. First of all, you need to store your data somehow. Because it doesn't make sense to train anything if you don't have data. With cloud, and very briefly about it, you you can have a lot of options. You can have key value storage, relational storage as managed one, install something yourself. But the basics is you actually have so-called blob storage, when you can store your file binary objects and then retrieve it by a key, by a path to this file. Sometimes people think about it like a file storage on your Windows machine in directories. It's not like that. All the directories are only emulated. All you have so-called a bucket, just kind of a basic object where you will then store all your files. And then for every file, you have a key. And the API works. You can put a file by a key. You can retrieve a file by a key. And you can retrieve all the files by a part of the key. And then it emulates the directories. Does it make sense so far? No questions? Okay, please whatever. Yeah, and we wouldn't focus on the storage itself, but the whole idea is if you go to the cloud, storage is cheap relatively to other things, and maybe you don't need to care about this as much. So you just save it there, and that's it. And another thing, it's important to understand, there is the more and more move to this separation of storage and compute. What does it mean? In a typical data centers, you have PCs, and you don't have a lot of flexibility. So all your CPUs are always running, you always have this electricity, and then you kind of like attach these arrays with HDDs, blah, blah, blah. But the idea is to kind of like, for example, you have your, let's say, Hadoop cluster. You kind of like, if you want to store more data, you are like out of capacity, you just buy another server and put in. So with the cloud, you deal in a little bit different paradigm. So you store your data, and then when you need compute power, you spin up virtual machines and perform some computations. And even like you can do it also with Hadoop environments. But enough about that. So if you rent a single VM, let's like skip it a little bit. I will go fast here. And if you have questions, please stop me and ask. You just choose a machine type. How many CPUs do you need? How many like memory do you need? Then you choose the persistent disk. So the idea is, again, you can have your persistent disk separated from your VM. So then you stop VM, you stop paying for the VM, but all your data are safe. And the data can be, for example, Jupyter notebooks and these kind of things. Then the question, how many of you have worked with Jupyter before? Okay, good. But, okay. So Jupyter notebooks, and again, please ask questions. If I'm using some terms you don't understand, ask, otherwise it kind of like doesn't make sense for you. Jupyter notebooks, it's actually some web interface for Python environment when you typically prototype your ML models. I don't know whether I explained it correct, but. Huh? With Jupyter, mostly Python, but yeah, not only. So like with Zeppelin, you can, yes, deal with Scala, but like. Julia. Okay. I've never tried it, to be honest, but yeah, I've kind of like all think about like Python and Scala, but maybe. Are you using Julia? Sorry?
Why Jupyter versus other editors?
No, it was just an example. I'm kind of like, you can use whatever. My point is that like, it's not a good idea to store your training data in persistent disks, but you can store some like, some temporary files. So if you use any other, kind of like things for prototype, and you can store them there. But the idea is you create a virtual machine, do some training, then you stop it, and your persistent disk is with you. You pay for it a little bit, but like not much. Yes, and then you can come back and recreate the VM from that previous point and continue your work. That's it. And then you can also create an image of the machine. Image actually is an operational system that is on the machine. You can, but like I have slides for that, sorry. So yeah, this is the typical workflow. You move your data. You do something locally on your laptop, for example, if you are allowed, because like some companies doesn't allow you actually to, move any data out of the data center or out of the cloud, because in the cloud you also can have this secure perimeter, like a secure network that nobody can kind of like go in. Then you take care about the virtual machine, then you deploy it, perform your training, and destroy the virtual machine. And we will kind of like cover it in a few things. So yeah, this is kind of like about the machine types. I mostly covered it. The whole idea is the principal pay as you go. So for example, we bill you per seconds. Yes, there is some minimum. You need to consume at least 1 minute. But then, like if you have consumed like for 5 minutes and 5 seconds, you pay for 5 minutes and 5 seconds only. It's kind of like a nice model. And then again, kind of like you can get different discounts. The more you use, you can get like the discount for committed usage, but like I don't think. Yeah.
Educational institutions, do you offer discounts or?
Sorry?
Educational institutions and universities?
Yes, we have some programs. We even give something for free. Ask me afterwards, and we can get in contact, and I might kind of like help. But I don't know a lot about like sales, so kind of. This is just an idea about some prices, but like whatever. Now about the images. About the images, so you can. Yes, I have this feeling. Okay. Sorry, guys.
Is it workflow?
Yes. May I double check it? Because the problem is I was kind of like sharing with my other account, because I couldn't connect my Mac. I'm sorry. I'm awfully sorry. Okay. This is very bad. Sorry. Okay. Okay, let's continue with what we have. What do you think? If I will show it from my Mac, would it be good for you, or you wouldn't see anything? If I just put my Mac here, would it work? No? No.
The stuff that you show is kind of complementary. It's not.
We have made some changes in TensorFlow API, and I have some better slides about that. Sorry, guys. I'm really sorry. May I ask, like, for the password again?
ACD.
ACD.
1, 2, 3, 4, 5. That's it.
This one, yeah.
Yes.
Okay. Thank you.
Do you need a VGA keyboard?
But you should connect.
USB-C. No. I need a
But you should
USB-C
connect
one.
to this.
Yeah. Sorry. ACD. 1, 2, 3, 4, 5.
I have one for display.
That's it.
No, wouldn't work. Sorry.
Yes, that's
Yeah.
it.
The new one.
I have a new one. Yeah. Sorry. Okay. Connected. Now I need to go to slides. Yeah, I haven't shared the. Yeah. Thank you. Sorry. Okay, sorry. Let's continue with what we have somehow, like it's not updated. The problem is that also I cannot log in with my kind of like Google account on this laptop, and so I'm trying to share it with my private account, and it's kind of doesn't go through. Okay. Okay. Let's go, and then at some point I will switch to my Mac, most probably, and try to explain it, because like we have done some changes in TensorFlow APIs, and I have updated my slides. Sorry for the mess. Sorry, guys. Nevertheless, where were we? We were here. So yes, the images. You need to create the like the image is actually the operational system you use on your virtual machine. And again, you can like try with some free images like Ubuntu or like Debian or whatever. So we have some Linux images. We have now, that is not on the slides, that is on the new slides. We have like the deep learning images in beta when you kind of like have the CUDA and like already installed, and all other like nice stuff like TensorFlow and PyTorch. And we have also like some premium tier images when you like pay a little bit licenses fees. Like it's kind of, so the renting cost of your VM is a little bit higher, but you can get access like even to, for example, Microsoft images, like I mean Windows, like Microsoft SQL Server or whatever. So this is kind of like the idea about it. The whole idea is why it's nice. If you're an ML team, you really need to take care about your environment so that your kind of like production environment is the same as your development environment. Why is it the case? Because when you actually train models, you deal with numbers, you deal with flawed numbers. And so actually kind of like you don't want that you train your model with one version of, for example, one library on one operational system even, like, or you know, on different versions of Ubuntu. And that's how you train your model, but in production you have a little bit different environment. It can, you know, cause some unpredictable, like, you know, some unpredicted things that like your models would suddenly perform like worse than it was performing like in the training, in the training environment. So it's very important to have like very fixed environments at every stages when you are developing your models. And the cloud actually gives you the ability to control that in a very easy way, because you can follow this, you know, principal infrastructure as a code. You can define an image of your OS starting from a clean Ubuntu, and very clear kind of like define what kind of libraries you want to have installed. I mean, and you can do it with Docker, but you can actually do it like on a like lower level kind of. And then you can like replicate it for production and like for testing, for prod, like for like on all stages you have. So this is kind of the idea of it. And the idea is that you can also have your private images. So actually you can save an image later for later, and like all people in your organization can create VMs based on this image. So this is kind of the idea how you can very easily control your environments without kind of like investing additional time and costs. And the second idea, when you are creating VM, you can also provide an additional startup script. So that's actually kind of like the things that will be executed during the VM creation, and startup parameters. These things, this is actually environment variables that VM can get access to.
Sorry, what's the GC?
Sorry? Where? It's Google Cloud Engine. So it's actually this service that gives you the ability to rent VMs. Because like we have a lot of services, and this is the one of them. Sorry. Yeah.
GCS.
It's Google Cloud Storage. So this is storage where this is blob storage I was talking about like in the beginning. So you can just store files there and kind of like. Yeah. So you can have, for example, this startup script not locally, but save it to the storage bucket, so like everybody can use this file later. One.
Sorry, are you going to share the slides later? Because it's really hard to read it from here right now. So are you going to just make it
Yes, most probably yes. I mean, via the conference all organizers, yes. I hope I will share like the updated version. Okay.
I have one question.
Yeah.
If I use the same versions of libraries, why should I expect some different output?
Now, if versions are the same, that's nice. But my point is that it's very important to like take care about it. So like that you have the same versions and every stages. So that's what's exactly the point. And that's sometimes hard to achieve because like you need, you know, to control this. But like actually with the cloud, it's easy because you can just like code it. So kind of like what do you want exactly, and you get it. So this is kind of the main idea. The first use case that's come to my mind, at least when I look at it, is what can you do with that? You can use it, for example, so first of all, you can use it just to train your model now. And you can provide, like, for example, this, like the trainings like command in the startup script, where you can now very natively, for example, scale for hyperparameter search. If you just perform a grid search, you can like scale it in a moment. So you just kind of like create a script that like, you know, spins, I don't know, 100 VMs. And like every VM gets its own hyper parameters. It trains the model, saves the result to the, for example, Google Cloud storage, including the binaries, and that's it. And then you kill the VM. That's the important stuff. I have. Okay, what's going on now? Okay. Let's keep the persistent disks. Let's talk a little about GPUs. This is now like not in beta as far as I remember, so again it's kind of like a bit old slice, but the idea is that you can actually pretty easy get a GPU and attach it to your machine. But not only GPUs. This is not relevant anymore because we have these deep learning images in beta. You can also get a TPU. What is a TPU? Exactly. So this is our own ASIC that was developed in Google specifically for TensorFlow workloads. And this actually, I mean, I have some details here, but it gives you kind of like incredible performance. But that's an important thing, and I want to talk about it. Sorry. Okay, yes, this is the example of some benchmarks. So actually, like there are like this is maybe one of the best of the benchmarks. So when you kind of look at it, you always need to look at the training time and training costs. And like what people are doing, they're comparing for some, bless you, for some specific models, different setups of like different hardware on different providers and these kind of things. So you can like easily go there and kind of like check it out. But the whole point is that sometimes people are a little bit overhyped and then come and tell, okay, we know what we need. We need neural nets and TPUs. I mean, I will talk a little bit later about it, like on my second workshop. That's not exactly the case and why it is. But like from engineering perspective, the idea is that, first of all, some workloads, including actually the inference, they are better suited for CPUs. Some workloads, they are better suited for GPUs. And only specific workloads, they are very well suited for TPUs. Since otherwise, for example, if your batch sizes are small, if you are using your custom ops and so on, you wouldn't see any gain in performance, but you will just overpay for the accelerator. So you need to be in a certain stage to go for GPUs, and you need to be even in a more developed stage to go for TPUs. So this is the idea. But TPUs are extremely powerful device that is nice to use, and I mean you can like just look at the slide. I'm not going into it, but this is kind of like obvious. So first of all, there is a certain list of supported TensorFlow ops. So even not all TensorFlow ops are supported on TPU. And the problem is that if you have like this not supported operation somewhere in the middle of your graph, you kind of like would experience big problems because like you cannot compile it on these low-level codes that would be kind of like ported on the TPU, and then like you wouldn't see any increase in performance. Same kind of like here. So for example, if you are using your custom ops that you write in C++, but you do not optimize them for GPU on the low level, then again you kind of like might not see any boost in performance when you go for GPUs. Sometimes, like if your batch sizes are small, so you kind of like, spend some time on like sending data here and there. Again, that's not the case, and we will see a very nice example later on. I hope at least. Sorry, it's not. It's yes. I was just checking the time, but this example will be in the new presentation. Yeah, this is the example how you train the model, and then like here you just like shut down the VM when you are done. It's kind of important thing. A lot of people who just move to the cloud forget about it, and then they're surprised by by the costs. If you don't shut down the VM, you keep paying even if you are doing nothing.
Why do you pass keep alive true in the first place? I mean, why isn't it sort of the default that it finishes? So in the first step, when
If not, this is the environment variable. I just, this is just an example. I just pass it, so it's kind of like, I just pass it as a startup
See, in your
parameter.
script,
Yes,
you
yes,
say
yes,
shutdown.
yes. And then I add it in my script.
But what if, let's say, the script has a, let's say there's an error and it never gets to this last step?
No, I mean like you shouldn't include the training. So I mean the bash script kind of like it should be pretty easy. And then it invokes, for example, some Python process. And then if you have an error in Python process, yes, it dies and then you continue. So kind of like it's okay. But then kind of like, yes, you are right. I mean, the idea is this is the ideal stuff, but then actually, like the point is that you can also kind of like add additional checks. So for example, you can have like alerts, okay, this VM has been running like for like a few hours now or whatever. So like you can add additional configurations not only on the VM level. That's it.
Sorry.
Yeah.
You might give an example like for batch size, recommended batch size for each of the three. Like when you talk about small, what can you give another example?
It's a very tough question. Let's talk a little bit about it later. I have like some slides about it, but I mean, it's very generic one. So the short answer is I can't, sorry, because it depends. But like so just to give you an idea, what is the small batch size? The small batch size is actually how it works. Let me address this question later, because like it's actually a very good question. Okay, and the last thing about the VMs, every cloud provider, I mean, at least in the top 3, actually have so-called preemptible VMs. I mean, we at Google call them preemptible VMs. AWS name them, I believe, spot instances, but whatever. The idea of preemptible VMs is you actually pay much less, like sometimes like 5 times less, but this VM can be easily preempted. So like there is no SLA on it. If somebody needs VMs in this zone, so zone is just like a data center, think about it like that, the VMs would be killed. That's why it's called preemptible, would be preempted. And you have only 30 seconds, to stop your stuff going on there. Why is it good for training models? Because like with training models, sometimes it's okay if the VMs gets away and then you get it back like in a few hours. Whatever, you maybe don't care so much. You will still finish the training at some point. But like you pay much less, and sometimes it's a good idea to do this. And for example, at Google Cloud, you can not only get like preemptible VMs itself, you can also get preemptible GPUs and even preemptible TPUs now in beta, I believe. So and this is nice because like then you pay much less for that. But the problem is, if the instance has been preempted, you kind of might want to continue training based on it. How you can do that? I mean, when you get the instance back. There is kind of like one of the things where actually the TensorFlow can help you. Again, TensorFlow is a great framework. I have some marketing slide here. Like this is the amount of like GitHub stars, whatever. But actually, the idea of TensorFlow is that why is it good? First of all, it's very suited. It was designed for distributed training, and it was designed for like different platforms. So like when you train your model, like with TensorFlow, you can kind of like inferences on like different operational systems or like on different devices even. So this is kind of like things that are implemented by design, and this is kind of like very nice sometimes very nice to have, because again maybe like you don't have a use case for that, maybe you don't want to inference your model on Android or whatever, but if you do, that's a good idea. And I will kind of like a little bit talk about it later. Yeah, but yeah.
There was written that TensorFlow has a high-level API. Is something new in TensorFlow, because as I know, it has some low-level APIs.
Yes, it has low level. Yes, exactly. So this is the idea. I will have a slide about it, I hope, and even in this old version. Yeah, but the idea is that it has like low level APIs that are written in C++ or even like in CUDA, like for GPUs, for example. But especially now we have this TF data and TF estimator API. One of the example we are talking about here. And in a lot of cases, especially if you're like in the beginner, you don't need to deal with this low-level stuff anymore. But like kind of like that is this high-level APIs, so like low-level APIs, if you like, I mean, there is some hierarchy, but like the lowest level that are actually kind of like very well optimized for specific devices. So divided by device, I mean kind of like, for example, GPUs, like NVIDIA GPUs. So these things, but like most probably you will never like take care about it. And
Hold on. So regarding the preemptible yes. So say I'm training a model. Will it stop in the middle of training and give it over to someone else, and then will I have to go back and do same startup work that I usually do to start training it, or will it automatically just
yeah, exactly. Good question. Please save it for 10 seconds, because like that was exactly what I wanted to tell about. So if you are using TF Estimator API, it's actually this one of high-level API that takes care about a lot of things, like you don't need like to place your variables anymore. You don't work with like TF graph and TF session anymore. If you have heard about it, so like you don't deal with that. You have like very high-level API that like takes care about like a lot of things. One of these things is the automatic creation of checkpoints. And what's a nice thing for our use case if you want to train on preemptibles? Then, when you recreate this preemptible, and you deliver your code there, TF Estimator will automatically detect that, okay, I have some checkpoints, and it will restore from the last checkpoint and continue the training from this point. And like, just imagine how convenient it is, because now you don't. And the nice thing, you even don't need to take care about like saving these checkpoints. I mean, you just like tell when you create an estimator, actually when you create a train spec, or like how often do you want to create this eval spec? Sorry, how often do you want to create these checkpoints, and that's it. Just to warn you, don't create checkpoints for every step. Sometimes people try to do this. The reason is it's not a good idea, because actually creating checkpoints takes time. Especially like, for example, if you train on GPUs, again, creating checkpoints takes CPU time, GPU is idle, and it's kind of like slows your whole training pipeline. So you need to find some trade-off. For example, you create like checkpoints on a certain schedule, like on certain intervals, and even if the instance was preempted like in the middle of this interval, okay, you don't care, because like you will continue from the last checkpoint, you will restore from the last checkpoint. So like the idea is don't create checkpoints too fast, too often. I've seen it like that people are doing this, and sometimes they even hit the Google Cloud Storage quota, because their job was very fast. They have, I don't know, 100,000 steps, and then they were like hitting too many requests to Google Cloud Storage to save all these checkpoints.
Is that totally manual setup, or do you have some model for optimizing the number of checkpoints?
No, I mean, this setup is manual, but like, I mean, yeah. Okay, and the idea is that now like TF Estimator, when it's actually can natively work with Google Cloud Storage. So now, again, you kind of like provide the path to the Google Cloud Storage when you want to store your model, like finally trained model with binaries, as well as all these checkpoints, and that's it. And then everything works out of the box. Enough about that. Let's switch to the TensorFlow, to distributed TensorFlow. So the idea is, sometimes you need to scale because you have too large data sets, or they do not fit in memory. If you like use some other frameworks that actually kind of like require to fit the whole data set into memory. How can you scale? You can scale vertically by having more and more VMs, but at some point you need to stop. Why is it the case? I actually kind of encourage you to see this very nice blog post if you haven't seen this. It was like a research released by OpenAI. The idea is, you must probably have heard about the Moore's law, haven't you?
Yes.
Yeah. So the Moore's law, what does it say? It says like that every actually 1.5 year, the amount of transistors per like some square doubles. and it means that like computational capacity that we have, it actually doubles. What the guys have done in their research, they tracked, I believe, last 6 or 7 years of like ML research, and for certain points in time, they took the the state-of-the-art model at this certain point in time, and they estimated how, like, single floating point operations you need to train this model. And then they can like have this nice graph. But the idea is that this thing actually follows the exponential path. So what it means that the amount of the computational capacity you need to train state-of-the-art model, whatever it means, it like doubles a certain period of time. And kind of like the surprising thing is, remember, for Moore's law, it doubles every 1.5 years. How do you think, how it doubles for ML, this amount of flops you need? Huh?
Every week.
Every week. Oh, okay. Not really every week. Every 3, I mean, but yes, it's kind of too fast, I think, if it has been doubled every week for last 7 years. So like, I mean, these guys have estimated it like roughly 3.5 months. But it's still like pretty short doubling period, I should say. So like, I mean, if you're interested, have a look. Yeah.
Budget held constant? Or
No, it's not the budget. It's exactly it's the amount of flops you need to train the state-of-the-art model. So like, I kind of like I can't include like this graph here because kind of like all this IP rights, but I can give you the link. So please read. This is a very nice research, and it's kind of like pretty easy to read. And just to give you an idea, for example, to train the neural machine translation model, again, state of the art, you need 80 petaflops days. What does it mean? So if you have some device that gives you a petaflops, then you need 80 days. And just for your understanding, like a TPU, the most powerful device that you can imagine now, gives you, okay, TPU version 2 now, we have version 3, gives you like 180 teraflops.
It's today.
Huh?
It's today only. Today only.
Current.
Why? What do you mean by?
Days today. Not the next year. Next year will be much more.
Much more, most probably, yeah. But like, I mean, still, it's kind of like, I mean, 80 petaflops, just to give you the idea, it's kind of like, it's something astonishing. So like, I mean, you need, if you have like petaflops, it's actually a supercomputer. And you need 80 days of this supercomputer just to train one model.
Multi-computer, like supercomputer. Like Google system.
But it's actually a supercomputer. I mean, if you have it.
There is one computer very powerful.
Okay. But like, I mean, still, so kind of like, the idea is that you need this computational power to train your models, and you cannot scale vertically. So at some point, you need to switch to distributed training, because kind of like these kind of things. And secondly, sometimes just your data doesn't fit into memory anymore, and you need to deal with that. And TensorFlow was designed for these things, and actually that's exactly what I want to discuss. How is it handle this? Let's skip this. So a few words about, so there are like 2 types of data parallelism. Of parallelism, sorry. One is data parallelism, and let's talk about only neural nets now. So this is the standard stochastic gradient descent. I kind of sorry, maybe it's for some of you it's a little bit too complicated, but the whole idea is just to make it simple. If you look at it, what are you doing during the training? So you actually take, so like first of all, you never, with stochastic gradient descent, you don't deal with the whole data set. You take a subsample of your data set that is called a batch, and then you estimate your model, your forward path, you create your goal of the forward path, you estimate your kind of like predictions for this batch. You compare them to your labels, you calculate the loss, and then based on this loss, you calculate the gradients. It's how much you should change your weights, and you kind of like go backwards updating weights in your model.
Frameworks do that for us, so we don't.
Yes. The frameworks do that for you now. But the idea is that, I mean, that's just to explain how it works. But the idea is that when you calculate this loss, you average it across all examples in your batch. What's nice? I mean, it's like, first of all, we are kind of like lucky that stochastic gradient descent works, that we can train on like some random batches. But what the second thing we are lucky, if we look at it, it kind of scales more or less perfectly because it's distributed by design. Again, we were just lucky. So what can you do? You can just divide your batches now in a small sub-batches and deal with every batch on single machine. And then you need just to synchronize. So like this whole formula is just can be executed in distributed mode by design. And that's how actually distributed TensorFlow works. If we look at this slide, you have your own, I mean, a lot of data. You kind of shuffle them across the workers. Then every worker creates a sample mini batch from its own portion of the data. Then you run the stochastic gradient step. And then the master aggregates the gradients and like sends the gradients back. What is the bottleneck? The bottleneck here.
Combination.
Which combination?
Aggregation.
Yes, aggregation. Thank you. Exactly. So the problem is that you still, like on every step, your workers should be synchronized. So before you kind of like calculate the loss and gradients for the step, you need all your workers to finish this forward pass. So you still have this synchronization point. People deal with this sometimes, and if somebody is interested, there are like some nice papers on arXiv. I'm not going deep into it about like asynchronous stochastic gradient descent, but like there are like a lot of stuff actually how you compensate for these delayed gradients. So like the good thing is that you can kind of like make your workers deal completely asynchronous with like all steps, but the bad thing is you need somehow to compensate for these delays that are coming from other workers, because now you kind of like some workers might be ahead, and there is like some ideas how to deal with that, and sometimes they work. Just to give you some idea. Okay, now we have like old slides. Let me talk maybe without slides if you don't want to look at my Mac. So the idea is that you have two different, you have the data. Now we need to deliver the data to our model. How can we do this? TensorFlow has very nice API called TF Data API now, and the so-called dataset API. And with dataset, how you work with data with TensorFlow. Sorry, I'm trying kind of like to improvise because I don't have slides anymore. So the idea is you save all your data in files. And TensorFlow creates list of files. And the idea is that TensorFlow, since we now deal with stochastic gradient descent, the good thing, we don't need to have all the data in memory anymore. We only need to have a batch. So, how it works now? You create a list of files, and you only need to handle a list of files in memory, and these dataset APIs have this like API called kind of like list of files. And then you can have like a few transformation of these files. Like for example, it can be TF records or CSV, so you need decode every record. Then you can like apply some map functions, whatever. And then you send it to the device. You combine it in batches and send it to the device, the accelerator. First of all, the first question, very important to understand. If you train with GPUs, all the data processing and kind of like data preparation is done on CPU. And so how it works typically, and I kind of like have some slides which illustrate this optimization. So the idea is, but now let's just follow my hands. Imagine this is the accelerator and this is the CPU. In basic mode, how it works, your CPU starts preparing your data with TF data kind of like call. When it's done, it sends the data to GPU. Now GPU start doing some stuff. When it's done, it sends us back to CPU. I mean to CPU's kind of sends us to parameter server, so-called, that updates the weights, and then we continue. What is the problem here? The problem is that sometimes when CPU is preparing the data, GPU is idle. And if preparation of the data takes some time, then it's kind of like not a good idea. And if you sometimes look at the TensorFlow profiling kind of like visualization, you can even see this. Kind of like preparing the data is kind of like a long step, and obviously the GPU is idle. How can you deal with that? Prefetch, exactly, thank you. And like with TF dataset API, now you have like certain call called prefetch. So, but this is only one optimization. So what you can do, you can just tell prefetch, and then when CPU is done with preparing the data, it sends us to the GPU, and it just immediately continues to prepare the new portion of data, the new batch. It continues just like to read it and whatever. But there is not the only optimizations you should to keep in mind. Sometimes, I mean, actually how it works, you read portion from your file, then what you do? You kind of like decode it, maybe you apply some map, some transformation, and then you like batch it. So kind of like group it into the batch, and then you send it to the device. So then actually how it looks, you have I/O, then you have some transformations. Again, you have some I/O, you read some another portion from the file, then you have some transformations, then you again have some I/O, you have some transformation, then you have a batch. What's the problem? Your CPU is sometimes blocked on I/O. How can you overcome this? The dataset API, now you can tell it, okay, I want to do like my reading from the file, my data preparation in by using multiple threads. You can like tell it, like use like, I don't know, 10 threads or whatever. Then like every thread now is stocked on I/O, so kind of like every thread has this problem, but the batch is created much faster. Does it make sense? Can you follow me? Okay, great. What else can you optimize for? Sometimes the problem is that kind of like, it might be the problem that like just reading from one file is slow. For example, you have some network latency or whatever. What can you do? Again, dataset API has things for that. You can use interleave. So you can tell, okay, I want to take small portion from the first file, small portion from the second file, small portion from the third file, and do this in a cycle. And then again, kind of like on every batch, you're kind of like not blocked anymore by the performance of your file system, because kind of like you have parallel calls to your file system. Does it make sense so far? Great. Then I have a question for you. Imagine I have a batch size, let's say 512, like examples. And my step was, let's say, 1 minute per step on a single machine. And now I switch to a distributed mode. Now I have 4 machines. What will be kind of like, what would you expect? What will be like the time like per global step now in a distributed mode? I have 4 workers. Okay, so 20 seconds.
I
Okay.
think it would be shorter because, as you said, you optimize for other things other than just throwing it horizontally. You said
Okay, what's your guess?
5 seconds.
5 seconds. 5 seconds? No, but like I haven't optimized. I have the same code. I just like changed to 4 workers now.
No, max you can set that was 15 seconds.
Okay, yes, kind of like. Okay, 15 seconds, 20 seconds, any other versions?
I said 5.
5. Hmm?
Maybe it's
15, yeah, 15, 20, any other versions? Okay, who is for 15? 2 of you? 3? Okay, for 5. Stick to 5, great, you know. Just make it for 20. For 1 minute. Why?
Because we make extra work to distribute data.
No. That's kind of very important, and I'm kind of like, I mean, that's really important to understand, and maybe that's the only thing you need to take from this talk. What is distributed training about? Remember I told you like this, CPU is dealing with like reading the data. You take your code and you deliver it to every worker, and then every worker start kind of like doing the same thing. But like, yes, kind of like, actually if you look at TF estimator, if you like would go and look into the code, it kind of like uses, I mean, some flags on the machine. So the machine actually knows whether it's a master and it knows its worker ID and these kind of things. And then TensorFlow has some conditions based on it. But actually, if you have batch size 512, what does it mean? Every worker will have batch size 512. So global step per seconds will be the same. It will still take you 1 minute per global step.
No, I thought you subdivided the batch into
No.
sub-batches.
It doesn't, I mean, it doesn't do this for you. I kind of see your reasoning, it's perfect. But like, I mean, it's kind of like, it's nothing wrong in your reasoning. It's just how TensorFlow is implemented, because other frameworks might be implemented in the other way. So I just want to explain how TensorFlow works, so that kind of like you adjust accordingly. So the idea is that every kind of worker will do the same, will execute the same code. But like what you might expect the conversions of your model, your model to be faster. So you might expect less global steps until your model converges. This is the first thing. The second thing, if all workers are doing the same, does it make sense? Because actually they're reading the same data.
So is it like we're splitting the one work on the like 4 workers, or
Same work.
Same
Yeah,
work
same
to
work
all
with
the,
4.
Yeah.
all the work.
So like it's actually they're not doing exactly the same, because if you look, for example, how like TF dataset like from list files whatever is implemented, it has shuffled through by default. So like when you create like a dataset from list of files, it shuffles it. And so like every worker now will kind of like, if you have only one file, then they will do the same. But if you have kind of like a lot of files for your data, they will do a little bit different stuff. So that's why kind of like you would, so actually effectively your now batch size will be batch size multiplied by amount of workers. That's the key. Second question, actually batches per epoch will be also the same by default, but you can address that because like TF dataset API has certain call called shard, and you can shard the data according to the worker ID. So for example, you can shard like at any step, but you can just tell like, okay, shard based on this. And then every kind of like worker will process only its piece of the data. And obviously, the earlier you shard, the better it is. Because then your CPU wouldn't do all this idle work to process the whole data and then kind of like skip it. Does it make sense? So kind of like everything is working by design as expected. And sometimes you wouldn't believe I really got like requests people are writing, your Google Cloud emulation doesn't work because kind of like now I have 8 workers, but like my steps per second hasn't decreased at all, or decreased like to a small amount of time. So kind of like, but that's exactly by design. You just need to know how it works, then you adjust your model like accordingly. That's all. Okay, that was that about TF data. Yeah.
So you sort of hinted that there's almost similar dynamics for the data files, right? Whether we have one very large file or, right, we could have, obviously we don't want one very large file.
Yeah, we don't.
But then we could probably go too far in the other direction too, right? You know, let's say the neural translation example, if we have one sentence per file, that would not be ideal either. So how do we find this balance?
Yes, how do we find this balance? We experiment. So kind of like, I mean, you can do some benchmarks according to your specific example. Like the documentation tells actually that 100 megabytes per file if you're using TF records is kind of good idea, but the answer is it kind of depends on what storage are you using, what is network latency, like kind of like you can be stuck in different things. But like sometimes, I mean, if you look, you really need to optimize your input, data input by pipeline, because this is the biggest thing. And then you really kind of like need to have a look what you are doing there. So, but I'm sorry, I can give you more specific answers. So.
No, but
But like, I mean,
file size.
having one large file is not a good idea, and having kind of like, you know, having kind of like too many small files also is not a good idea. But like, you can always add some preprocessing step. So like before, so just like split all the data, save them as TF records, and that's it. Last thing I wanted to say, sometimes you want to, do we have time or are we out of time? Sorry, we are out of time. Okay, guys. Last thing, sometimes you want to randomize your data when you have like files, and how you can do that. With interleave, when you kind of like start interleave data from different files, because sometimes your file are not randomized. For example, you have every file like for date, like it's partitioned, and you. Sorry. I just like, thank you. Actually, now I know that I'm out of time. So how you can do this? You can tell the model, first of all, at every point in time you can shuffle. But like when you shuffle only data that you have in memory. So you kind of like, you don't shuffle over the entire data set. So you can shuffle all the files, all the list of files you're going to read from. And then you can also implement this parallel interleave when you tell, okay, take small portions from every file. And you can kind of like define the cycle length. So the idea how it works, you tell, okay, I want at every point in time, I don't know, read from 10 files in parallel. And from every file, I want to take, I don't know, 5 records. And then it will do kind of like this, you know, moving cycles over all these 10 files. When one file goes to the end, you go to the next file, and it does it automatically. That's probably all I wanted to say. I'm sorry for a little bit mess with the slides. It's my fault. I will do better next time. Do you have any questions? One last thing I've forgotten to mention is actually sometimes it's not only about the data parallelization, sometimes it's about model parallelization. I'm not going to go deep into that, but what is model parallelization about? Because we have talked about data parallelization a lot. And you kind of like don't really deal with model parallelization in practice. But imagine you have a graph that have some subgraphs, so graph of operation that have some subgraphs. Then the idea is you can easily assign the subgraph to different accelerators, to different devices. And then every subgraph will be executed in parallel, and then you just merge the results. It's not the common case, but some models have this case, and you can do that. But again, probably not in practice, especially when you kind of like are in the beginning of your journey. Thank you. Any questions?